Hello everyone, welcome to course study on solid mechanics. In today's lecture, we are going to discuss the relation of effective length and the actual length, the concept of slenderness ratio and the limitations of Euler's formula. Okay, so first of all, we will discuss the concept of effective length. So what does it mean? It is the length of an equivalent column of the same material and the cross section with its both ends pinned or hinged, which has the same crippling load. Okay, so effective length is nothing but it is the length of an equivalent column. That column is made up of the same material and which has the same cross section. Okay, and the end condition should be a pin support or the hinge support. Okay, and it is subjected to the same crippling load. It is known as the effective length. It is denoted by the letter L suffix E. Okay, so it is denoted by the letter Le. Therefore, the crippling load in term of effective length is given by P is equal to PCR is equal to pi square EI upon L effective square. Okay, so this is the actually Euler's formula, and that Euler's formula is expressed in term of the effective length. So we are putting the value of effective length instead of length. Okay, so P will become PCR, both are same, both are the crippling load, and it is equal to pi square EI upon L effective square. Okay, or you can define effective length in other manner also. Okay, effective length is nothing but it is the distance between point of contraflexure on a deflection curve. It is the distance between point of contraflexure on a deflection curve. It is also a definition of effective length. Okay, critical load for column with various end condition can be related with the pin end condition through the effective length. Okay, so it means that we are going to relate the different end condition with the effective length. Okay, so the critical load for the column with the various end condition can be related with the pin end condition through the effective length. Okay, so this is the definition of effective length. Now we are going to discuss the relation between effective length Le and the actual length El. Okay, so all of you know that crippling load in term of effective length can be given by P is equal to pi square EI upon L effective square. Okay, therefore this formula we are going to use for the four end condition. Okay, so first end condition is one end fixed whereas other end is free. Second end condition is both ends pinned, or we can see it as a both ends hinged. Third end condition is one fixed end whereas other is pinned end, and the last one is both ends fixed. The last one is both end fixed. Okay, so remember that amongst the four, this second one it is an ideal condition. Okay, amongst these four end condition, the second one is an ideal end condition, and with respect to that we are going to compare end condition first, third and the fourth one. Okay, so for the first end condition we have one end fixed and other end is free. Okay, so we have a column AB. From the figure we have the column AB which has a length L. Okay, end B is fixed one and end A is subjected to an axial load P. Okay, so as end B is fixed and end A is free one, due to the axial load P, that particular column will bend in this particular manner. The column will bend in this particular manner. Okay, but as we have to compare this particular end condition with the ideal condition. Okay, so that particular ideal condition we have a bow like structure. It is a bow condition. Okay, so to make this particular deflection curve in this manner, we will extend this deflection curve in downward direction. We will extend this deflection curve in downward direction. Once you extend the deflection curve in downward direction, it will look like a bow. It will look like a bow, and it is similar to the second ideal condition. Okay, therefore the length of that particular bow will become twice L. The length of that particular bow will become twice L. Therefore the effective length will be the twice L. Therefore Le will become twice L. Okay, so you just put this value into the equation of crippling load. Whatever the answer we will get, it is nothing but pi square Ei upon 4L square. This is the value of crippling load for a column which is fixed at one end and which is free at other end. Okay, and at this particular load, the crippling or the buckling of that particular column will take place. After that, we have the second end condition, and that is the ideal one with both ends pinned condition. Okay, again we have the column AB, which is subjected to axial load P, and as both ends are pinned one, the effective length will become L. So Le will be the L only. So you just put the value of L into the equation of crippling load. Okay, again we will have the pi square Ei upon L square. Okay, so this is the ideal end condition. Now third end condition is one end fixed and one end pinned. Okay, so end B is fixed one, whereas end A is pinned one. We have the column AB. In that column AB, end B is fixed, whereas end A is pinned one, and it is subjected to an axial load P. Due to that axial load, the column will bend in this particular manner. The column will bend in this particular manner. Okay, due to the loading, due to the end condition. Okay, so in that case, we have the effective length 0.7 L. We have the effective length 0.7 L. Okay, therefore, if you put the value of 0.7 L, or we can see it as L upon under root of 2 also. This value of effective length is nothing but L upon under root of 2. Okay, or 0.7 L. So you just put this value into the equation of crippling load. We will have 2 pi square Ei upon L square. 2 pi square Ei upon L square. So this is the value of crippling load for a column which is fixed at one end and which is pinned at other end. And the last column we have both end fixed. Okay, so end B is also fixed and end A is also fixed one, and it is subjected to axial load P. Due to that load, the column will bend in this particular manner. The column will bend in this particular manner. Therefore, we have the effective length L by 2. L by 2 is nothing but it is 0.5 of L. Okay, therefore put the value of effective length into the crippling load. The equation will become 4 pi square Ei upon L square. Okay, so it is very important concept, and you have to remember the end condition, and for the given end condition you have to find out the value of effective length in terms of actual length. Okay, so this is the relation between Le and L. Now we are going to discuss the concept of slenderness ratio. Slenderness ratio is denoted by the letter lambda, and it is the ratio of effective length to the least radius of gyration. It is the ratio of effective length to the least radius of gyration. So we know that in column the buckling always takes place about the axis of least resistance. Therefore the moment of inertia I in terms of area A and the radius of gyration K is given by the following equation. Therefore, the moment of inertia in terms of area and the radius of gyration is nothing but I is equal to AK square. I is equal to AK square. Therefore, the radius of gyration will become under root of I upon A. From this equation, we have this particular equation. K is equal to under root of I upon A. But all of you know that the crippling load by the Euler formula can be given by pi square Ei upon L effective square. Pi square Ei upon L effective square. So you put the value of I, into this particular equation. So we will have P is equal to pi square E into AK square upon L effective square. Pi square E into AK square upon L effective square. Okay, so after making the mathematical arrangement, after making the simplification, we will have the final equation pi square EA upon whole upon L effective upon K bracket square. Pi square EA whole upon Le upon K bracket square, where Le upon K is known as the slenderness ratio, because as discussed earlier, slenderness ratio, it is the ratio of effective length to the radius of gyration. Okay, therefore the value of this Le upon K is nothing but lambda square. Okay, so as it is the ratio of two same quantity, okay, so the slenderness ratio, it has no unit, it is unitless. Okay, so this is all about the concept of slenderness ratio. In the next lecture we will discuss the limitations of Euler's formula. Okay, so we will stop here. Thank you.